So today we start section 4.2 where we discuss finding the area between a curve and the x-axis. And this might seem a little bit out of the blue. In the last section we talked about antiderivatives, and now we're just sort of switching into this sort of geometric idea. And if you're wondering why, just bear with me through section 4.2 and we'll see how all the pieces fit together in the next section. So the first thing that I want to talk about is, well, why? Why do we care about this? Why would we want to find the area between a curve and the x-axis? So just to give you just one small example of where this might be useful, if we look at the velocity of a car, and it's given by the formula f of t equals t squared in feet per second, so the velocity of the car at time 3, for instance, would be 3 squared, or 9 feet per second. Then finding the area between this curve, which is a curve of the function f of t equals t squared, and the x-axis, right, so this area of this region here that I've shaded, the area of the shaded region will tell us the distance that the car has traveled over that first period of 0 to 3 seconds. So the distance that the car has traveled during the time, or during that interval of time from 0 to 3. Okay, and so if we can figure out what that area is, we'll know exactly how far the car has traveled. And we could probably estimate this pretty easily because this looks sort of roughly triangular shaped. So we could get an okay estimate just by forming a triangle here, although it'll be a little bit of an overestimate, because if we were to try and turn that into a triangle, we're going to be including some area here, which technically isn't under the curve, and so it isn't really going to add to the distance. And so this would be a little bit of an overestimate. But this is why it might be interesting to find this area underneath the curve. And so if this was something really important, you need to know exactly how far it was traveled in that period of time. That estimate can give you a guess, but it can't give you the exact answer. And so this leads us to a more important and more pressing question, which is how? How do we find the area underneath the curve if it's sort of a strange shape like this? So we're going to answer this first for some easier shapes, and then see if we can use that to maybe get a sense of how to do it for more complicated curves. So in this first example, let's look at the function f of x is equal to -1/2 x plus 3. And we want to try to figure out the area of the region bounded by the two axes and f of x. So the two axes being the x-axis and the y-axis. Now this is a line, right? This is a y equals -1/2 x plus 3 would be a line with a slope of -1/2 and a y-intercept of 3, going all the way back to day 1 slope-intercept form. And so we've got 1, 2, 3. We've got a y-intercept of 3 and a slope of -1/2, which means every time I go down 1, I need to go over 2 to the right. 2. Then I go down 1 again and over 2 more. And I go down 1 again and over 2 more. This is when I'm going to hit the x-axis. And so this line, of course, is going to go on forever, but we're really just interested in the area that's bound by this line and then the two axes. So we're looking for this triangular, the area of this triangular region. And this isn't roughly a triangle like we had up here. This is actually just a triangle. So all we need to do to find this area is use the formula for the area of a triangle. And if we've forgotten that, it's 1/2 times the base times the height. This is a right triangle, so it's super easy to find this area. The base is 6 units, so it'll be 1/2 times 6 times the height we see is 3 units. And so the area ends up being 1/2 of 6 would be 2. 1/2 of 6 would be 3 times 3, which is 9. Okay, so this we could actually just compute because that straight line gave us a shape that we have an area formula for already. Let's look at another example. This time we're going to look at the function g of x is this piecewise function here square root of 4 minus x squared for x values between -2 and 2. And g of x is the linear function x minus 2 for x values between 2 and 4. And again, we're going to try to find the area between the curve and the x-axis. So let's try to get a sense of what this graph would look like. First of all, for x values between -2 and +2, we're going to be using this equation here. I'm just going to rewrite it out using y as our output instead of g of x. So y is equal to the square root of 4 minus x squared. What the heck does this look like? Maybe right off the bat you might not be sure what this looks like. I'm going to try to rewrite this by squaring both sides. If I square the right-hand side, the radical symbol will go away and we're just left with 4 minus x squared. And finally I can rewrite this as x squared plus y squared is equal to 4 by moving the x squared term over to the other side. This hopefully looks familiar. This is just the equation of a circle. And since we had only taken the positive square root instead of plus or minus the square root up above, that really means we just want the top half of a circle. So this graph is going to look like the top half of a circle between -2 and 2 for a circle that's centered at the origin and has a radius of the square root of 4, which is 2. Okay, so this graph really just looks like this. Okay, and it's going to hit the x or the y-axis here at 2. Alright, so this is going to give you sort of the first part of this graph, and then for x values that are bigger than 2, we're going to use this linear equation, g of x is equal to x minus 2. And so, do we have any holes or anything here? Well, no, because when we plug in g of 2, right, which is the very first x value here, we'll get g of 2 is equal to 2 minus 2, which is 0. Which lines up exactly with where the circle ended. So it meets up nicely, and then after that, this is basically just a line with a slope of 1. Right, so we'll have a point at 3, 1, right? G of 3 would be 3 minus 2, which is 1. And then we'd have a point at 4, 4 minus 2, 2. So 4, 2. Okay. And this line would keep going, but we're really only interested in the area between -2 and 4. I guess maybe it doesn't keep going. The function's not defined after 4. Alright, so here's our shaded region here. We've got a semicircle first, and then we've got a triangle. Okay, we know how to find the area of each one of those. So just find the area of that semicircle, then find the area of the triangle, and that will be your total area. It's easy enough to do. So we just need to remember our formula for the area of a semicircle. The area of a circle in general would be pi r squared. So the area of a semicircle would just be pi r squared divided by 2, because we only want the top half of the circle. And the radius of our circle, of course, is 2. Right, radius is 2. And so this would be pi times 2 squared divided by 2. That would be 4 pi divided by 2, or 2 pi. Alright, so that's telling us that this area here of this first part is an area of 2 pi. And then we have that the area of the triangle, we already said before, that area is 1/2 times the base times the height. The base is going to be 1, 2 units. The height is also going to be 1, 2 units. So this area is 2. So it's an area of 2. Alright, so all together, the area between the x-axis and the curve is going to be 2 pi plus 2. Area between the curve and the x-axis. Right, so again, if we have formulas for the shapes that are formed with these particular functions, then we can just use those formulas to find the area without too much trouble, as long as we actually know the formulas. Alright. Now, what happens if our line went below the x-axis? So far, in all the graphs that we've looked at, we've been looking at area that was above the x-axis, but we know that outputs of a function that are below the x-axis are negative outputs. So in some sense, we have or we can consider that area below the x-axis as being negative area, and we call that signed area. So when we talk about the signed area between a curve and the x-axis, we just mean any area that's above the x-axis, right up here, is positive, and any area below the x-axis is negative. So let's look at an example. We're going to try to find the signed area between the curve and the x-axis for the function f of x equals x minus 2 on the interval from 0 to 3. Right, remember this is a linear function, it's an x to the 1 power. It's got a y-intercept of -2, and it's got a slope, well we don't see a coefficient here, so let's assume it's a 1. Right, we've got a slope of 1, which means every time we go up 1, we're going to go over 1, up 1, over 1. And we're going to go as far as, we start at 0 and go up to 3. Up 1, over 1. Okay. Right, so this is what the line's going to look like. And it's telling us just to look at the interval from 0 to 3, so I'm not going to keep drawing the line to the left or to the right. But we see that this breaks up the area between the curve is going to be below the x-axis between 0 and 2, right, between x equals 0 and x equals 2, and it's going to be above the x-axis between 2 and 3. Right, so this part here, because it's above the x-axis, is going to contribute positive area, and this part below the x-axis, this shaded region here, is going to give you negative area. Right, and of course, area is always really something that's positive. It doesn't really make sense to talk about negative area, but when you get into applications in the future, especially in Calc 3 or multivariable calc, we'll see why maybe it makes sense for this area beneath the curve to be negative. Alright, so if we want to find this total area, well, we just need to add together this negative area here to this positive area here to get our total net area. Each one of these is a triangle again, so it's not so hard to find the areas individually. I'll start with the positive area up here. This is, again, for a triangle, it's 1/2 base times height. So it's 1/2 times, the base just has a length of 1, and the height just has a height of 1. So it's 1/2 times 1 times 1, which is 1/2. And down here below the x-axis, for my negative area, it's 1/2 base times height again. But this time, the base would be 2, and the height, see, this is where the negative sort of comes from. The height here, from 0 down to -2, is like a negative height, because it's below the x-axis. And so 1/2 times 2 times -2 would be -2 altogether. Okay, so the total area then would be given by adding these two together. -2 for the area below the curve, plus 1/2 for the area above the curve. And we can simplify this to -3/2, or -1.5. Okay, so that's what we mean when we talk about signed area. And for the most part here, in general, when we talk about area under a curve, we'll be talking about signed area. So anything below the x-axis will be negative area. Okay.